Hi, so let's talk about how do we find the function's characteristics from desmos to just, double check your results. So we're working with this subject function here, which is f of x. And I'm going to try to show you how to find out where this function is increasing, where this function is decreasing, where are the critical points, and how are we going to figure out the concavity, concave up, concave down, and inflection points just from this, okay? So the first thing to do is to be able to visualize the derivative from desmos. Okay, to do that you just type in f prime of x. Okay, oopsie, my bad. My 0 key is pressed for some reason. So I'm just gonna remove all this, f prime of x. Okay, so now that we have our function typed in here, I can turn off the original function by clicking on this. So that goes away. So now I can literally see my derivative function here in blue. The points where this blue function will cross the x-axis is where the critical points are. So you can already know the critical points here are negative 1.732 and positive 1.73. So I'm going to label them out. I'm going to call them x1 as negative 1.732. And I'm going to call x2 as my other critical point, which is going to be positive 1.732. Okay? So that's how I easily figure out what's happening. So now I want to see where this function is increasing. Well, that could be done usually just visually looking at the graph or by actually finding the values, okay? The intervals that we'll be interested in, okay, will be the interval from negative infinity up to the first critical point, which is negative 1.732. The other interval will be from negative 1.732 to positive 1.732. And then the last interval will be from positive 1.732 all the way to infinity. So as you can see, like in this interval, if you pick any point before, let's say negative 1.732, you see the graph is negative because it's below the axis. So I know the function is decreasing all the way from negative infinity to negative 1.732. That's a visual way of seeing it. But if you want to just test this value and see what's happening, so you pick a point before negative 1.732, so I can pick negative 2, and I already get a negative result. That's why I know that this function is going to be decreasing in this interval because the derivative is negative. So if you want to pick another point in between these two critical points, so that will be the second interval we're looking at. So you can pick x equals to 0. I can evaluate the value at 0, and that comes out to be 3, which you can also visually see from the graph is also 3. Okay, so that means it's positive, which means the function is increasing here. And you click on that, you pick a point after 1.732, so I can pick x equals to 2, and I see it's a negative number, so the function is decreasing again after this critical point. So this way you can easily say the function is increasing in the interval from negative 1.732 to positive 1.732, and the function is decreasing from negative infinity all the way up to this point, union 1.732 all the way to infinity, just quickly by looking at desmos. So that's what this would do for the first derivative, right? So now let's try to repeat this analysis for the second derivative. So I'm going to keep all this information here. You don't have to remove it. I'm going to start talking about the second derivative here. So I'm going to type in double prime of x. So now I have a graph of my second derivative here. Now to find inflection points, I would want to see where this second derivative is 0. So I can go here, and you can literally see those points where this graph cuts the x-axis at negative 1, 0, and 3, 0. So basically you have two inflection points. I'm going to call them x inflection point 1, which is going to be negative 1, and I'm going to call the second inflection point x inflection point 2, which is going to be just positive 3. So I have all these values here. Now I have to check the concavity in these intervals from negative infinity to negative 1, from negative 1 to 3, and from 3 to infinity, okay? So as you can see, if you pick any number before negative 1 and evaluate the second derivative, so I can pick, let's say, negative 2, I see the second derivative in that interval is a positive number, which means the function should be concaving up in the interval from negative infinity all the way up to negative 1. So moving on in the second interval, between negative 1 to 3, I can pick x equals 0, so I can evaluate at 0, and I know it's negative 3, which means the function should be concaving down in that zone, okay? So we know function is concaving down between negative 1 to positive 3. Now the last interval is going to be for any x value above 3, so I can pick 4. So desmos is just going to quickly spit out the number to be positive, which means the function is concaving up in that zone. So to summarize, the inflection points are -1 and 3, and the function is concaving up in the interval from -infinity all the way to -1, and then the interval union 3 all the way to infinity. Okay, the function is concaving down in the interval from -1 to 3. And that is how simple it is, right? So now if you want to see all these pairs, I'm going to remove this. I'm going to open up the whole graph. Now I'm going to try to label all those points that I found out, okay? The first point that we found out was a critical point, x1. And if I type x1 bracket comma f of x1, you can see it already labels that point here. Okay, so I'm going to label that point as a minima, because that's what I see from the graph very easily, right? I can test the other point, which is x2, which is our second critical point, and evaluate the function at that point and put them in a combos. That will be a maxima. Okay, so I know that it will be a local maxima, of course, but that will still be a maxima, so I can label that way. Now inflection points are kind of hard to see here, but I can, because I have the information, I can type them in here as well. The inflection points, the coordinate is xif1, and the function's value at that function's value at xif1. And by the way, if you want to go on the subscript, you type the underscore. It will take you down on the subscript, so I write those numbers. Of course, you can choose different names. I'm making overcomplicated names. You can just choose A, B, C, whatever you want to call them, and it will be easier. So this is your inflection point number 1. That's that. And now the other point is going to be x inflection point 2, with the function's value at the x inflection point 2. So that's why you see the other inflection point over there. We'll label that as well. And that's how you solve this problem using Desmos in under, I don't know how much time did we take to record this. It's under 5 minutes, roughly, I would say. So that's it about for this video. Thanks for watching.